Okay. Now we'll continue our lecture today where we have left last time. So I will draw the equivalent circuit of the transformer. Let me draw the equivalent circuit of the transformer. Equivalent circuit of the transformer looks like this. This is okay. Okay, so this is the primary side I'm drawing. I will draw the equivalent network here. Now, okay, so this will be your primary side. Okay, now here this is equivalent circuit referred to primary. So this is Z1 plus Z2 dash. Okay, then your current flowing will be I1. As usual, voltages will not change. They will be V1, and your another voltage will be V2, and number of turns will be N1 and N2. And then we have current flowing on the secondary side is I2. So this is just a second. This is referred circuit to, this is equivalent circuit referred to primary. So I will write it down. This is referred to primary. So we have referred this to primary. Values are as usual. Now, if same thing I want to refer to the secondary, then what are the changes I need to do? Okay. So just a second. I hope everybody is familiar with this type of circuits. Small changes I need to do. Now here, just a second. Just a second, please. Bear with me. Okay. So sorry for. So now what I will be doing, I will be drawing the equivalent circuit referred to the secondary. So I will just join this, and we have the same things here. Nothing will change. So here, what I will draw, I will draw to equivalent circuit. So that will be Z2 plus Z1 dash. Okay. So this is the equivalent circuit, and here it is I2, I1. Rest of things will not change. So this is equivalent circuit referred to. This is equivalent circuit referred to secondary. Okay, this is equivalent circuit referred to secondary. So this is what we will do in the absolute system. Absolute system, we have referred this to primary, secondary, and we can draw even both sides. We can draw this impedances. Now let's come to the next. Next we have a transmission line, and this is third. What we'll compare between per unit system, and this is third is transmission line. Now in transmission line, In per unit system, we know we can easily draw it. Transmission line is represented like this. Draw a line. These are here. If you remember last diagram, which is our reference diagram, single line diagram. So it lies between bus bar 2. Sorry. So it is between bus bar 2 and bus bar 3. You can have a look at the single line diagram. So this is a transmission line which lies between bus bar 2 and 3. In power, you should always remember, in power system, transmission line is represented by always you should remember, it's remembered by nominal pi and nominal t. We have done this in power system 1. T, but preferable is nominal pi, that I have already told you. So this is how we have to draw in case of the per unit system. Now, if we draw in absolute systems, let us draw first T model in case of absolute systems. So this will be very simple to draw T model. Okay. So this will be first resistance, reactance, then will we have shunt capacitance. Here it will be grounding. This is just revision. You know how to draw this. We have drawn this in power system 1. And this is again the reactance. So this is your resistance. This is your reactance. Set T. We are drawing T model. This is your reactance. So if we see that single line diagram, it lies between bus bar 2 and 3. That already has been mentioned above. So this is R by 2 and this is L by 2. If you have to take the reactance, then you can take reactance accordingly. You can include J, but L by 2 is fine here. So this is also R by 2 and this is L by 2 and this is lumped at the center capacitance. Now, if we have to, because I have told you we normally neglect these shunt branches, so this further can be drawn like this. We can include resistance, we can include reactance, and then bus bar. Okay, so further we can simplify between 2 and 3. We do not include shunt branches because very small amount of current flows through them, as I already told last class. So we'll write this R, L, R by 2 and R by 2 will get, because this branch has been cancelled. R by 2 will become R and L by 2 will become L. Now, if still we need to consider this as a lossless line, so I have already told you what is the condition of the lossless line. Resistance will not be included in the lossless line, like this, between 2 and 3 bus bars again. So we include only reactance L. Inductance L, we can use the reactance. XL is equivalent to omega L 2 pi FL. So this is for the lossless line. Okay, on the similar grounds, if we have to draw a pi model, this is for figure for T model. Now similarly, if we have to draw this for the pi model, like this, this is for the pi model. This is the ground. You can have a common ground for them. and this is your capacitance, half here. So this is C by 2, this is C by 2, and this we know is a complete resistance. This we know is a complete reactance, R. This will be L. Again, this is between 2 and 3. This is the preferable model we use. Number of nodes becomes lesser in this case. And then similarly, we can use lossless line and other things that you can draw. So this is a nominal pi configuration, we can say. Okay, I hope this is clear. Mumin?
Yes, sir. समझा.
Okay, so let's move further. I will add a page. Okay, now you should always remember transmission line is represented by short line when shunt branch is ignored. Transmission line is represented by short line when, you should remember, when shunt branch is ignored. When you do not include the shunt branch, then you always know the transmission line will be called as a short transmission line. So what will determine the type of a line? So FL, multiple of FL, that you know in the power system one-way study, whether it is short, medium, and long. The ranges I have given you. What are the ranges of FL? So you should remember those ranges, and then you can decide accordingly what type of transmission line there will be. So fourth is synchronous motor. Now, in case of synchronous motor, how we represent in the per unit system? Very simple. Okay. This is, you can see per unit, this is connected. Synchronous motor is connected at bus bar 4. The reference single line diagram you have to see. It's not here. So you can see that. So this is in per unit system. Now, let us draw this in the absolute system. How we can represent this in the absolute system? In absolute system, we have same bus bar. Then we will be having the motor resistance. We will be having the motor reactance. And okay, then we'll be having the motor itself. Okay. So here we have motor resistance, reactance of motor. This is as usual bus bar 4. This is in the absolute system. So we can write this Rm. And if you want to include reactance, then it will be JXM. Otherwise, LM you can also use. It doesn't matter. And then you have the excitation, motor excitation. Sorry. Just a second. Okay. So we have motor excitation. We'll call it, what we are going to call it? We are going to call it EM. So we'll call it EM. Okay. So if we have to draw for a lossless line, so we should always remember condition for a lossless line is what? Lossless line, Rm will be equal to 0. Resistance is neglected in that case. So that will be equal to like this. We have bus bar where we have reactance only, and then we will have excitation only in that case. So it is here, and this is your small excitation. I'm drawing it. This will be reactance only. So we call this reactance JXM, and the same motor excitation EMF EM. So this is for the synchronous motor. For first is for the per unit system, how we represent. Second is for the absolute system. So we can again see that in a absolute system, lots of things have to be included, and single line diagram is, as usual, the concise way of representing the power system components as usual. So Rm here is what? Rm here is resistance of motor. Resistance of motor. Xm is reactance of motor. Reactance of motor. And then your Zm is impedance of the motor, which is equal to Rm plus Jxm. Okay. Now, if we have to represent the generator as usual, if we have to compare between generation is for motor is a load, generator is for generation. We can use that for generation. So we can draw it like this again. Compare them. This is the reactance. Okay. Okay. So for a lossless line, this is the terminal voltage. We know this already. This is generator reactance. Ig is the current flowing through the generator. And this is the excitation of the generator, Eg, plus minus. So this is for generator. In case of motor, we have just seen okay. So we have reactance here for the motor, sorry. So motor is going to consume the power, whereas generator is going to deliver the power. So when current enters the positive terminal, so that clearly means that it is absorbing the power. This is Im. Current is entering the power positive terminal, it will absorb the power, whereas current is leaving the positive terminal, it will deliver the power. Again, I will write for your reference. This has been already cleared in network. Current is leaving positive terminal, hence generator will deliver power. So current in case of motor, current Im is entering positive terminal, hence what's going to happen? Hence motor will absorb the power. it will absorb the power and it will act as a load. So very clearly, this we have already seen in the network. Okay. Then last is the induction motor. I will add a page again. Now last is fifth. Induction motor. Now induction motor, if you can see in your single line diagram, which we have already referred, is connected to the bus bar 4. Is connected to bus bar 4. You can see here it is connected to bus bar number 4, and this is induction motor IM. So this is representation in the per unit system. Now if we are going to represent the same in the absolute system, what we have to do, we have to include resistance. So this will be resistance, then reactance, and when it is connected to equivalent circuit, we can draw. First, we can draw the circuit of this one, then we can draw either of the equivalent circuits. So here, let me draw first. Okay. So this is your resistance, reactance, primary side, secondary side, and this is JX2, R2, JX1, R1. Now if we draw the same, because it's a static load, we call it load with only impedance. I already told you it's called a static load. Now if I draw the equivalent network of this one, so R1 will be this one, JX1, R2, JX2, then we can have primary side, secondary side. We call it a static load. Load will have only impedance. So here we can have resistance, reactance, refer to primary I am making. Resistance, equivalent circuit, refer to primary. So this will be okay. Now this side, what I can do when I refer them, R2 will be here, J2 that will go on the other side. It will become a short circuit here. Sorry, this will become a short circuit. Once this is a short circuit, so what is going to happen here? This is, I'll write again, this is R1. As usual, we are going to refer it to primary side. So there will be no change on the primary side values. Secondary side will become R dash, JX2 dash. And since we have voltage here 0 here because it's short circuit now, so voltage here will be also 0 volts. So then how we can do it? We can write it like this in simple terms. Okay, like this. Oh, sorry. Okay. Okay. Okay, fine. So what we can do here, since it's a short circuit, here it will be a complete short circuit. So we can combine these resistances. These resistances will become like this, and reactances will become like this: R1 plus R2 dash and JX1 plus JX2 dash. So when I have told you that load which consists of only impedance is termed as a static load. So induction motor is a static load. Load which consists of only inductance is called the static load. So this is very clearly static load. हाँ जी मोमिन, इज इट क्लियर? सिंक्रोनस मोटर का इंडक्शन मोटर का क्लियर है? इक्विवेलेंट
Yes, sir. I
डायग्राम.
submit.
हाँ,
Yes, sir.
आई
I
थिंक
submit.
यू हैव स्टडीड दिस इन द मशीन में आल्सो, आपने पढ़ा होगा. तो यहाँ why I am showing you this, I want to compare between the absolute system and the per unit system. Per unit system is very concise. See, bus bar connected to induction motor. Now absolute system, if you have draw circuit, will be like this without transferring to primary side. If you draw it to primary side, then circuit will be like this. Circuit will be finally like this. There will be lots of components in this case. But in case of per unit system, will not have such components. Okay. Okay. So next, we'll be talking about the impedance or the reactance diagram. Okay. And please remember that whenever we draw only the per phase circuits. Per phase. Why? Hanji Mumin, why we draw the per phase circuits only? What's the reason? Mumin.
Yes, sir.
Why we draw the per phase circuits only here? What's the reason?
Per unit circuit के लिए हम इसलिए यूज करते हैं क्योंकि
Per phase. Tell me.
पता नहीं.
Because I have told you that system is a balanced system.
Yes,
When
sir.
the system is balanced, whatever will we draw in the first, that we can be extended to the other phases also.
Yes, sir.
Please remember this. So next heading is impedance diagram. It is impedance diagram. Now you can very clearly see I have drawn one system. This is a single line diagram, and this single line diagram of a simple power system. Very simple power system is this. This shows a single line diagram of a simple power system. The symbols represent the following. Number 1 means, I will write here only, number 1 means, 1 here means generator. Sorry. Generator number 1, that means number 1 generator. Number 2 here means generator number 2. Number 3 means here generator number 3. So this is the meaning of 1, 2, 3. Okay. Now then we have T1 very clearly here, star connected, neutral, grounded. So T1 is transformer 1, and T2 is transformer 2, and then in between transformer 1, T1 and T2, this is a transmission line also we have. We have a transmission line. Very clearly, this is your transmission line. Okay. Now, प्लीज रिमेंबर दीज थिंग्स. उसके बाद हम इस डायग्राम को बना लेते हैं. इसको हम फिर सिंपलीफाई भी करेंगे. तो नॉर्मली यू शुड रिमेंबर, मैं नटशेल में ही लिखूंगा, डिटेल में नहीं लिखूंगा, मैं खाली बताऊंगा यहाँ पे. आई विल टेल यू ओनली. सो इन ऑर्डर टू कैलकुलेट the performance of the system under load conditions. So if we have to calculate, performance of system under load conditions. Okay, then what we need to do, if we have to calculate this, that under load conditions or upon the occurrence of fault, या अगर हमारे पास occurrence whenever the fault will occur in a power system, then we need to use the single line diagram इसको कहते हैं. We need to use the single line diagram, and that will be drawn single phase equivalent. That means that will be drawn on the per phase basis of the system. Okay, then all those single phase circuits can be combined together, equivalent circuits combined, which will show the various components as we have shown in the figure. So I will again repeat. Just a second. In order to calculate the performance of the system under load conditions or whenever the fault occurs in the power system, single line diagram is used to draw what? To draw the single phase equivalent circuits of the system that combines the equivalent circuits of the various components, which is shown in the figure number 2. That means second figure I have shown here that shows it. Now, number 1, you should remember in this case how we have to draw it. Please make it sure. Point number one is impedance diagram on the single phase basis. When we are drawing the impedance diagram on the single phase basis for use under balance conditions, as I have told you, whenever the diagram is drawn, that has to be drawn under the balance condition. Why? Because we say that power system is designed under balance conditions. Also, it is operated under the balance conditions. That can be done by using the one line diagram. So next is, second, I have told you magnetizing current of the transformer is usually insignificant, because I have told you the magnetizing current is very small as compared to the full load current. So I'll write here magnetizing current of transformer is usually insignificant. That is, it's not important. Why? Not important compared to the full load current. Compared to full load current, the amount of the magnetizing current is very small as compared to the full load current. Here, the shunt admittance is usually omitted so what we do, shunt admittance is usually omitted when we draw the equivalent circuit. That means when we draw the impedance diagram, so we don't include the shunt admittance. Why? Obvious reasons. The current flowing through the transformer is very small as compared to the full load current. This was the one reason. Second point you should know. Second point is that resistance is often omitted. We don't use the value of resistance is often omitted. कब इसको omit किया है? Resistance is often omitted when making the fault conditions. During fault conditions. Okay, so resistance is often omitted under fault conditions. Its omission includes, जब इसको हम, when we neglect it, then what will happen? Its omission will include that there will be a small error in the power system, small error, but the error quantity is so small that whatever the results we are going to obtain during the analysis of the power system, that will not have much impact on that. So that's why we neglect the resistance during the fault conditions. I will remember it. I will repeat it again. Resistance is often neglected under the fault conditions. Its omission, when we neglect it, its omission will not have a significant effect on the analysis of the power system, because error introduced in the system will be very small, and that's not going to influence the other results of the power system. So I will write it. Its omission induces, or sorry, its omission introduces small error, yeah, a negligible amount of error, some error, but the results may be satisfactory, since the inductive reactance of the system, since inductive reactance as a system is greater than resistance. You should always, this I already told you in the power system one also. So whenever the resistance is neglected during the analysis of fault conditions, neglecting the resistance will introduce a small quantity of error, but that error is not going to influence on the results, and the results, in other words, will be satisfactory, because the value of inductive reactance is very high as compared to the resistance. So this was the second point. Now, third point is loads which do not involve the rotating machines have little effect. That means those which do not have the rotating machines, those who are the static loads are there. Static load, just now I told you example of static loads, they will have little effect on the total line current during a fault, and also can be omitted. So next we can write loads which do not include rotating machinery have little effect. किस पे? On the total line current. So on the total line current, they will have a very little influence during a fault, and hence they also can be neglected. And hence can be neglected. That means whatever the static loads we have, which do not include rotating machineries, will not have much influence on the load current or the line current. In other words, those can be neglected also. Next is now the representation. Motors and generators, how are they represented? Motors and generated, are represented while I'm talking about while we draw the impedance diagram, how we will represent them. Motors and generators are represented as voltage source. How we represent them? As voltage source and with series resistance and inductive reactance. With series resistance and inductive reactance. So next what we have, motors and generators, when we are drawing the impedance diagram, will be represented as a voltage source, number one, with series resistance and inductance. See, after the impedance diagram, we are going to draw the reactance diagram. In reactance diagram, we are going to neglect the resistance also. For the time being, since we are talking about the impedance diagram, so impedance diagram includes resistance and inductance, inductive reactance, otherwise, so that has to be included here. So motors and generators, when we are drawing the from a single line diagram, when we are drawing the impedance diagram, motors and generators will be represented by a voltage source in series with a resistance and an inductive reactance. Okay. In the case, if we have a synchronous motor, loads are always included in making fault calculation. If we have a synchronous motor, that has to be remembered. See, since the generator, why? Because the generated EMF will contribute to the short circuit current. So if we have a synchronous motor SM, so that has to be included during fault conditions. That has to be included during the fault conditions. Since why? Since we have generated EMF from the synchronous motor, since the generated EMF will contribute to short circuit current. I will again repeat it. If we have motors and generators in a single line diagram, so how we have to represent them in the impedance diagram? By a voltage source that will include a series resistance and an inductive reactance. And if we are having a synchronous motor we have to include under fault conditions. Why? Because the synchronous motor, as you know, that it will generate the EMF. Synchronous motor will generate the EMF, and that generated EMF will contribute to the short circuit current. That generated EMF will contribute to short circuit current. So next is transmission line. I hope this is clear, Mumin.
Yes, sir. As much.
Okay. Anybody has a doubt? They can raise their issues. Next is the transmission line. Transmission line, I have already told, is represented by pi model. So loads are assumed to be passive. That means loads are assumed to be passive in a sense that it will not include the rotating machines, and are represented by resistance and inductive reactance in series. So transmission line is very simple. Transmission line is represented by pi model. ठीक है. Loads are assumed to be passive. What does that mean? That means those loads which do not include rotating machines or rotating machine parts. So transmission line, as usual, will be represented by the pi model. Loads will be assumed to be passive, and then not involving the rotating machine parts, and are represented. Now when we have to draw the impedance diagram, they will be represented by what? They will be represented by resistance and inductive reactance. So they will be represented by resistance and inductive reactance. That will be in series. Series connection will be there. Resistance and inductance. Okay. So next, बीच में चला गया ये. You have to manage it. ठीक है. Sequence wise इसको manage करना. ये बीच में चला गया पेज कोई. Anyway. So I will repeat it again. Transmission line will be represented by a pi model very clearly. Loads are assumed to be passive. What does that mean? That whatever the loads are, that they will not include the rotating machines, and that load, whatever the load will be there, they will be represented by a series connection consisting of resistance and inductive reactance. Next is neutral grounding will not be included. Next point is neutral grounding impedance. do not appear in the impedance diagram or also in the reactance diagram. Why? Can anybody? Mansha is there. Roll number 26.
Yes, sir.
Can uh, roll number 26 is there?
Yes, sir.
Can you tell me why neutral grounding impedance do not appear in the impedance diagram? Why? What's the reason?
The neutral carries very little current
That means
or
what?
negligible current.
Since we are assuming the balance condition, so there is no case of current flowing through the neutral. हम assume कर रहे हैं ना balance conditions.
Yes, sir.
Okay, fine.
Then negligible current passing through the neutral can be neglected.
As balance conditions are assumed. So that very clear, that itself clears that when the balance condition assumed, no current flows through the assumed, no current flows in ground under balance conditions. Okay, so I hope this is clear about the. Now here, what are the important points? Magnetizing circuit we will not include because current will be very small as compared to full load current. Shunt admittance will be omitted, not considered. Resistance will not be also neglected during fault conditions because its its neg its omission or neglecting resistance will introduce a very small error in the calculations because a reactive inductive reactance is much larger than as compared to the reactance. And loads which do not include rotating machine parts will have a little effect on the system, on the line current particularly, and can be neglected. Motors and generators will be represented by a voltage source in series with a resistance and inductive reactance. A synchronous motor under fault conditions will be included because they contribute, their EMF will contribute to the short circuit current, that's the fault current. And transmission line represented by the pi model. Rotating loads which have rotating machines will not be included, and loads will be represented by series resistance and series reactance, inductive reactance. Neutral grounded will not be included. Sorry. Okay. So this is the diagram. You can have a look. See what we have done here. We have this is the system, actual system. For this system, we are drawing this is the impedance diagram. This is a one line diagram, and this is the impedance diagram. Have a look here. So generator number 1 represented by source, voltage source, series resistance and reactance. Generator number 2, because there is a parallel, all the three are parallel. This is a bus bar. So second, this generator number 2 again represented by a voltage source, series resistance and inductive reactance. And then we have a load. Load is also in parallel. Load is represented by, because it's not a rotating load, it will be represented by resistance and reactance in parallel. So it's very clear load A is here. So load A is here. Here is generator 1 and 2, load A. Then coming to here, we have a transformer T1. Transformer T1, primary side represented by resistance, reactance, secondary side resistance, and we have included shunt. This part we can neglect. In next diagram, we can neglect this shunt part. I am going to draw that. After that reactance diagram मैं जब draw करूंगा तो I will neglect it. आपको दिखाने के लिए ये वाला part, this part you can neglect. Obvious reasons are there because the current flowing through this is very small, so shunt admittance can be neglected. This is primary side of transformer. This is secondary side of transformer 1. After that transformer, we have a transmission line. You can see transmission line here. Now transmission line is represented by pi model. So we have resistance plus reactance, inductive reactance, impedance here, and half of that C and C by 2 will be here. So that will be represented by the transmission line. This is a very clearly a pi model. After that, we have a transformer 2, again primary side represented by series resistance and series inductive reactance, series resistance and series reactance on the secondary side. Then we have a shunt side. Shunt side can magnetizing circuit, that is the shunt admittance, again can be neglected for the transformer T2. Then next we have a parallel one generator 3. We have here generator 3, we have here impedance. You can include resistance also. I have not written here, but you can include resistance. Here it should be resistance. You can draw it like this: resistance, reactance, and then voltage source. And load again will be represented by series resistance and series reactance. So this is the way we have to draw the impedance diagram for any single line diagram. Hanji, is there any doubts? Momin.
No, sir. Clear, sir.
Okay, is there any doubt what we have, how we representation? So this is all for today. Next we will go for the reactance diagram. Our class is almost over. 2-3 minutes hai. So you can send me this. First of all, I have to stop this recording just now.